Welcome back to CMOS RF integrated circuits. Today we are going to start with a new module, bandwidth estimation techniques. Today's lecture we are going to discuss method of open circuit time constants. Basically in the earlier module we looked at the MOSFET. Now we are going to start using the MOSFET, and first of all we are planning to work at 1 gigahertz, 2 gigahertz, 5 gigahertz, right. So, we need to be able to estimate quickly the bandwidth of a given circuit. So, this module, that is the basic intention, that given a circuit, look at it, do a few calculations, can you estimate the bandwidth that your circuit will perform at. Now, when we do this bandwidth estimation techniques, first part, it assumes that the system is a low pass system. I have this basically this technique has been developed, and it is a very quick solution to a very difficult problem. So, normally when you want to estimate the bandwidth, how do you do it? You have this complicated circuit, you first find out the Laplace transform. Okay. Find out the DC gain, and then you have DC gain times some poles and some zeros. Right. This is how your Laplace transform looks like, and now what you want to do is to find out, let us say, the 3 dB bandwidth. You want to find out omega, j omega, such that this quantity is equal to half. You need to find out omega such that this entire quantity is equal to half. It is a very complicated thing, very complicated business, and to do this properly you would most probably need a computer. You would have to solve some equations in many roots, many roots are involved in these equations, and you really have to put in a lot of effort. Now, as an alternative, what we have got is a quick solution. It turns out that it is very accurate also. This method is called method of open circuit time constants. Now, before I start with the method of open circuit time constants, I am going to tell you when it works, when it does not work. It works when the system has only poles. That is the basic most important limitation that we have got, that when the system has only poles, no zeros, then method of open circuit time constants works very well. Second thing is that all the poles have got to be real poles complex conjugate poles create problems. Okay. Complex conjugate poles can be worked with in the OC time, open circuit time constants. I call this OC time constants method. You still can work with complex conjugate poles, pairs of poles, but it does not happen to give you very accurate results anymore, somewhat lower accuracy, right. So, these are the main two limitations. What does this mean? This means that you can't work with inductors and capacitors at the same time. Since our MOSFET has a lot of capacitors, this basically means that as soon as I put an inductor over there, I most probably won't be able to work with open circuit time constants anymore. It is not going to give me the most accurate result anymore. All right. So, these are the limitations. All right. Plus points are, of course, it is very quick to for hand computations, and it is very accurate. Usually, if you abide by these rules, it is very accurate. All right. Works when all poles. What does this mean? This means that you have got a low pass transfer function. Everything is a pole. So, not even complex conjugate poles. So, your Bode plot has got to look like this, something like this, right. This is how your Bode plot needs to look like for this method to work. Okay. Now, how does it, what's the story, what do we do? So, the method is this, that if you have got a circuit with lot of resistors, capacitors, GMs, control voltage sources, control current sources, whatever you want, right. You have got this circuit with you, and you want to find out the bandwidth of this circuit, bandwidth of the transfer function of the circuit. So, what you have got to do is, you have got to pick out every capacitor. You pick out every capacitor. Suppose I have got a capacitor, these are all the, I have got a capacitor between these two nodes. So, you stretch it out of the network and remove the capacitor. Okay. Remove all the other capacitors inside, and then basically remove means open circuit. Open circuit all the capacitors inside, open circuit the capacitor which you are holding outside, and you measure the resistance looking inside. Now, there are no capacitors in this, presumably there are no inductors in this circuit. So, you will only see a resistance, you will not see anything which is capacitive or inductive, you will see a resistance. So, what is the resistance here? You measure that resistance, the capacitor that you removed, let us say it is C, you measure this R in. So, R in times C gives you a time constant. Okay. You do the same thing for all the different capacitors in your network. You do the same thing for all the different capacitors in your network and tabulate your results. Okay. Now, the claim is that the 3 dB bandwidth is the reciprocal of the sum of all of these time constants. So, these are called the open circuit time constants. You open out all the capacitors and measure the time constant for one of the capacitors. You do the same thing for every one, sum all of the open circuit time constants, 1 by of that should give you the 3 dB bandwidth in radians per second. All right. The result, surprisingly, it is a very neat, very quick computation. The result that you get out of this is very quick, very accurate, because it ignores zeros that may or may not have been there. Usually the result is an underestimate. Zeros are only going to increase your 3 dB bandwidth. The presence of zeros will only flatten out. If you have got a 0 over here, you have got something like this, right, if you have got a 0 at this point. So, zeros are only going to increase your bandwidth. So, as a result, the method of open circuit time constants is usually an underestimate of what could have been, right. Now, what I am going to do, I have brought my calculator over here and I am going to do an example step by step, work it out. So, first I am going to do an example step by step, work it out, then my plan is to prove this method to some extent, and then we will do more further and further examples. All right. Suppose I have a MOSFET device and the following are the parameters of my MOSFET device. I have pushed a current through the MOSFET device such that GM is 10 millisiemens, RDS is 2 kilo ohms. Somehow notice that GM times RDS is typically a number around 20. Okay, this is fairly true over all technology nodes somehow. It only gets worse, does not get better. So, at modern technology nodes 90 nanometers, 45 nanometers, this number GM times RDS is actually much lesser than 20. You might get something like 10, 8, something like that. That is probably as high as you can get it. Little bit older, you will get actually 20. Okay. So, GM RDS, I am giving you these two. GMB, let us say it is 1 millisiemens. All right, these are my DC parameters. Let us forget about RG for now, gate resistance, let us forget about it. Then I have got my capacitances. Let us say CGS is 200 femtofarads, CGD is 50 femtofarads, C drain to body is 100 femtofarads, and C source to body is 150 femtofarads. Let us start with these numbers. Okay. Why is source to body less than drain, more than drain to body capacitance? I have put C source to body as 150 femtofarads, drain to body as 100 femtofarads. Why is source to body capacitance more? Because the drain potential is higher. So, drain to body is more reverse biased than source to body. So, the junction is wider, which means drain to body capacitance will be lesser, source to body capacitance will be more to respect to each other. Okay. So, these are the numbers we are going to work with for this exercise, all right. And let us say that I have got a voltage source which is inseparable from its source impedance. that is my source, and I am planning to drive this into my load. My load is 2 kilo ohms in shunt with 1 picofarad. Okay, and I am planning to design this amplifier. So, as a first cut to the amplifier, that is going to be my first example. I am going to do this. Right, this is my plan, and I want to estimate the bandwidth of this amplifier. Okay. So, let us put all the capacitors in place, and then one by one we are going to pull out the capacitors and find out the time constants for each of these. So, what are the capacitors that we have? We have got CGS, we have got CGD. See, source to body is irrelevant because source is already at ground. We have got see drain to body, and we have got the load capacitor. And the MOSFET, in addition, we have GM, we have got RDS, and GMB is between body which is grounded and source which is grounded. So, the current going through GMB is going to be 0. So, you can safely ignore that. Let this be over here. All right. So, first step, let us pull out the capacitor. First of all, let us pull out the capacitor CL, okay, and we want to measure the resistance when we pull out CL. So, CL is outside, and we want to measure the resistance looking in over here with respect to ground, but of course, and what else? All the other capacitors are nulled, which means all the other capacitors inside are removed. Okay. So, what do I see when I look in? Naturally, you are also going to null V in. Okay. You have nulled out V in. What do I see? I see, first of all, I see 2 kilo ohm looking downwards, and looking into the MOSFET, I see RDS of the MOSFET, right. CGD is not there, CGS is not there. So, whatever is connected to the gate is really irrelevant. So, I basically see RDS of the MOSFET in parallel with the 2 kilo ohm that is at the load, and my RDS happens to be also equal to 2 kilo ohm. So, RL is 1 kilo ohm, which means that the open circuit time constant is 1 kilo ohm times 1 picofarad, which happens to be 1 nanosecond. Right, I am going to write it in terms of picoseconds, so 1000 picoseconds. All right, done, fine. Next we are going to work with CDB. CDB is very similar to CL, basically you see RN. You do not see anything else. What is the value of CDB? CDB is 100 femtofarad. Okay, that was quick. Next, we are going to work with CGS. you remove all the other capacitors, you remove CGS and find out what is the resistance that CGS is going to see. On one side, CGS is going to see 1 kilo ohm. On the other side, CGS is going to see the gate of the MOSFET, which has infinite resistance. So, basically it is going to see 1 kilo ohm in parallel with infinitely large resistance. So, it basically sees 1 kilo ohm. Okay. Now, what have we got left over here? We have got CGD left. So, that is going to be the last one. I kept it for the last because it is also little tricky to do this one. Why is it tricky? Because it is no longer with respect to ground. All the other capacitors are with respect to ground. Okay. So, this is what we have got. Let me redraw it. This is what we have got, and I need to find out the resistance seen between these two terminals. So, I apply a voltage source between these two terminals and see what is the current going through, right. Now, before I do that, I would like to do something. I would like to redraw my circuit with a change in the ground terminal. So, before I redraw my circuit, let me connect all the grounds together. Okay. And now, what I want to do is, I want to call this particular node as my ground. See, ground is any, you can reference to any particular terminal. So, ground is just a word for the reference potential. So, instead of choosing the source as the reference potential, why don't I choose the gate as the reference potential? You can always do that. And as soon as I do that, I am going to now, I will have to redraw my network a little bit to make it look convenient, right. So, this is how I am going to redraw my network, right. So, what is the impedance when I look in over here? Now, do you remember how to do this? Well, if you have done your analog circuits and remember how, you would probably remember this configuration, which is basically identical to this. Okay. And the input impedance looking in from the drain, then I have got RS sitting on the source, is basically GM times RDS times RS plus RDS plus RS. That is basically the precise expression for the resistance looking into the drain. Okay. If you do not remember this, I suggest that you memorize this. This is a very, very useful formula, very useful formula. No. Okay. So, I suggest that you memorize this situation and this formula. It is going to come up again and again and again. So, it is better that you just memorize the expression. Anyway, so what is going to be my resistance looking into the network over here? So, what is RGD going to be equal to? Here it is basically identical to what I have indicated, just that RDS is no longer just RDS, it is RDS in parallel with 2 kilo ohm, that is all, right. So, my RDS is 2 kilo ohms in parallel with another 2 kilo ohms is basically 1 kilo ohm. So, what you are going to see is GM, which is 10 millisiemens, times RDS, which is now 1 kilo ohm, it is 2 kilo ohm parallel with 2 kilo ohm, times the resistance attached to the source, which is another 1 kilo ohm, plus another 1 kilo ohm, that is RDS, plus the resistance attached to the source, which is another 1 kilo ohm. So, 10 millisiemens times 1 kilo ohm happens to be a factor of 10 times 1 kilo ohm, that is 10 kilo ohms, plus 1 kilo ohm plus 1 kilo ohm. So, this is equal to 12 kilo ohms. So, tau for the gate to drain capacitance is 12 kilo ohms times 50 femtofarads, and that should give me 600 picoseconds, right. And then my next step is to add up all of these taus. So, if I add up all of these taus, then my total tau is 1900 picoseconds, which basically tells me that my 3 dB frequency, the bandwidth, is 1 by 1900 picosecond in radians per second, that is my quantity. So, that is 526 mega radians per second divided by 2 pi, and that will give me 84 megahertz. All right. So, it turns out if you do the simulation of this with these particular numbers, the result you will get is fairly close. It is going to be a little more than this. Instead of 84, maybe you will get 90, 85 to 90, something like that. This is basically the method of open circuit time constants. I did not spend much time on this, even as a tutorial, as an example workout step by step. I worked out every step of this. It took me about 12 minutes or so to work this out, right. So, it is fairly straightforward. As you get more and more practice, you will be able to do it faster and faster, and you basically get the bandwidth of your circuit. Now, next step, before I proceed further, next step is to prove this. How are you going to prove this? I mean, we can't just say that it so happens that it is fairly accurate and that is the proof. No, that is not the proof. The proof is this, that if you have got a lot of capacitors, then each independent capacitor creates a pole, right, and you can express your system. Remember, we are talking about an all pole system. So, your system is basically your DC gain divided by the product of all of the poles, right. Let us say each pole is coming from each capacitor. So, n capacitors, n poles. This is not really true, but let us say that is what happens. N independent capacitors do give me n poles. What is an independent capacitor? In our example circuit, we have got CL and CDB parallel to each other, they are not independent. Okay. You can club them into one whole thing, and that will give me one pole, right. So, that is why I said independent capacitor. Okay. So, we have got all of these poles, and if you simplify this, then basically you get 1 as all of the as the DC term, and for the first order term you get you get sigma S times 1 by SPI. Right. The second order term, you get S squared something like this, etc., etc. Now, at the 3 dB frequency, before the 3 dB frequency arrives, which term is important, which terms are not important. So, before the 3 dB frequency arrives, my gain is approximately going to be equal to ADC. So, 1 is always there, everything else is small. Why is everything else small? Because S is really j omega, right. So, as you increase omega, the contribution from the first order term increases. So, before the 3 dB frequency arrives, contribution from the first order term is not even there, right. That is basically the idea. So, at the 3 dB frequency, it has got to be, so if omega is small, omega squared is even smaller, omega cubed is even smaller, right. So, the higher order terms are even smaller than the first order term, right. The first order term is the largest at the 3 dB frequency. Therefore, the contribution of the first order term is all that matters, which means that the 3 dB frequency is the frequency at which the contribution from the first order term is equal to the contribution of the 0th order term, which means that the 3 dB frequency is such that the condition I wrote down here, 1 by SPI happens to be tau pi. Right, which means that the 3 dB frequency is 1 by the total of all of the time constants. Now, it so happens that whether I club two parallel capacitors or not, it does not matter. The time constant for the total time constant for two parallel capacitors is going to be the same. So, time constant of CL is something, time constant of CDB is something, time constant of CL parallel CDB is going to be the sum of the other two, earlier two, right. So, it does not really matter whether I lump them together into one parallel capacitance or not, which is why our technique basically worked. So, first I said that let us forget about all the independent capacitor business, and now I went back and said that yeah, you can have all the capacitors independent of each other. All right. So, this basically is a hand waving proof of my open circuit time constants technique. The next step is going to be to continue with my example. So, we started with this as an example and we continue and try to make a better amplifier. So, what you see in over here, the method of open circuit time constants, is that you can basically see for yourself which capacitor is contributing how much time constant, which capacitor is responsible for slowing down my system. So, which capacitor over here is the culprit? Why is my 3 dB frequency only 84 megahertz? Why can't it make it 1 gigahertz? Who is responsible? CL, right? It looks like CL is contributing 1000 picoseconds, all the others are much less in terms of their contributions. So, if this design needs to be fixed, I need to fix the time constant corresponding to CL. You agree? So, I need to see a low impedance when I talk about CL. From CL, I need to see a low impedance. That is basically what is going to fix my design, right. So, what is your guess? How do you create a low impedance? If you look into the drain of a MOSFET, you see high impedance. If you look into the source of a MOSFET, you should see low impedance, right. So, you have to add a source follower over here. That is what is going to get you the low impedance that you want. All right. So, let us modify our design. Let us say that I split the load into the resistive and the capacitive component, just for doing it, okay. And let us say I place the 2 kilo ohms over here, that was my load resistance, and the 1 picofarad over here. So, I am basically buffering, I am putting a source follower to drive the 1 picofarad load capacitance, okay. So, this is my new plan, new game plan. And I now have to work out what is the bandwidth of my new circuit. So, to work out the bandwidth of the new circuit, we need to place all the different capacitors. So, let us number my MOSFETs. Let us call this M1, second one is M2, okay. And I have got CGS1, I have got CGD1, I have got C drain to body 1, then I have got C gate to drain of the second one, C gate to source of the first of the second one, C source to body of the second one. What about C drain to body of the second one? It is irrelevant because both sides of that capacitor are at ground, okay. And I have got CL, which is 1 picofarad. Okay. So, this is my situation, right. What do I do? I am going to take each and every capacitor, pull it out of the circuit and find out the resistance looking in. So, to start with, let me start with CGS1. So, there is no change from my previous calculation, right. When I pull out CGS1, remember CGD1 is already not really there. The resistance I see is still 1 kilo ohms. So, there is no change from before, which basically means that I have got 200 picoseconds. Okay. So, this is done. Then CGD1, is there a change in CGD as far as CGD1 is concerned? When I added the new transistor, did things change as far as CGD1 is concerned, as far as CGD is concerned? Did things change? I still have the 2 kilo ohm over there. So, the resistance that I see is 2 kilo ohm. I have got what I used to have, and then I have got a new MOSFET over there. Okay. Looking into the new MOSFET, obviously I see infinitely large resistance. So, it makes no difference, right. So, nothing is going to change. Okay. CDB1, anything has changed? Nothing has changed. That is why I split it into pieces, right. Okay. Now, we have got a few new ones. I have got CGD2. CGD2 is really between the gate of the second MOSFET and ground. Okay. So, I pull it out, I apply a voltage over there. What resistance do I see? It is the same resistance as the drain to bulk of the first MOSFET. Which is 2 kilo ohms in shunt with RDS of the first MOSFET, which happens to be equal to 1 kilo ohm, total is 1 kilo ohm. So, I basically see 50 picoseconds. Right. Then next one is C source to body 2. What do I see, or even the load? What is the resistance that the load is going to see? as far as the load is concerned, it is basically going to see 1 by Gm of M2. Is that all? What about GMB? It is basically going to see 1 by Gm plus GMB. So, looking in from here, you see 1 by Gm plus GMB, this combination, right. Body is at ground, gate is also at ground, okay. Source is wiggling. So, you basically see 1 by Gm plus GMB. Gm and GMB come in parallel to each other. So, how much is 1 by Gm plus GMB? The Gm that I chose is 10 millisiemens, GMB is 1 millisiemens. So, 1 by of 11 millisiemens is about 90 ohms. I am sorry, yeah, 90 ohms. So, CSB, source to body, was 150 femtofarads, right. 150 femtofarads is 90 ohms, and as a result I get 14 picoseconds. Similarly, load also sees 90 ohms. So, 1 picofarad I see 90 ohms. So, I basically see 90 picoseconds. Beautiful. From 1000 picoseconds I have brought it down to 90 picoseconds with the addition of a few more. What else am I missing over here? CGS 2. All right. Now, this is going to be difficult because it is no longer referenced to a ground potential. So, let us do this separately. So, it is like this. You remove all the capacitors, touch those two nodes with a multimeter and find out what is the resistance that you see. That is what you want to do. Now, to do that nicely, what I would prefer to do is to dereference one of the nodes and make that the new reference. So, instead of referencing everything to ground, let me hook up all the grounds together right, and instead of calling the old one my ground, I am going to call this one my new ground. Right. So, now let me rearrange my circuit. My new circuit looks like this. Okay, that is how my new circuit looks. I want to find out what is the impedance, what is the resistance looking into the source. Now, to do that, what are these values, by the way? This was 1 kilo ohm, this was 2 kilo ohm. Okay. Now, to do that, first let me try to find out what is the resistance looking in this way as a first step. What do you see when you look in to the MOSFET from the source? There is a resistor over there. What do you think you are going to see? So, you replace the MOSFET with its GM. Okay. Is there any current going into the 1 kilo ohm resistor? No, there is no current going into the 1 kilo ohm resistor. So, therefore, the drop across the 1 kilo ohm resistor is 0. So, therefore, the current through the current source is also going to be 0 because VGS is 0, right. So, as soon as VGS is 0, the current going into the MOSFET is 0. So, the impedance looking in over here is infinitely large. So, basically you need not even worry about all of this. It is as if it is not there. Fine. All right. Now, I just have this, and if you go back to your analog circuits, the impedance looking into the source, when you have got the drain connected through a resistor to ground, gate is also connected to ground. This comes from a template. It basically looks like this: RDS plus RD divided by 1 plus GM RDS, right. This is also an important formula. I think you would be wise to memorize this. You would be very wise if you memorize this important formula. Okay. So, going by this important formula, what we have is RDS is 2 kilo ohms, RD is also 2 kilo ohms, divided by 1 plus GM is about 10, I forgot GMB, GMB comes in shunt with GM. So, I have got 11 millisiemens times RDS, RDS is 2 kilo ohms, right. And this basically, the denominator gives me something like 2 times 11 is 22. So, denominator gives me a factor of 23, numerator is 4 kilo ohms. So, basically the resistance that I see is 4 kilo ohms divided by 23, which is 173 ohms. So, 174, I am sorry. So, as far as the time constant is concerned, I have got 174 ohms, I have got a gate to source capacitance of 200 femtofarads. So, I have got 35 picoseconds. So, look at my new design. I sacrificed my 1000 picoseconds. Instead, now I have got 4 different capacitors, 50, 14, 90 and 35. I have obviously done better. My total tau now is 900 picoseconds from earlier, plus 189 picoseconds. So, I have got 1089 picoseconds. So, that gives me bandwidth of 146 megahertz. Right. So, we have done a fantastic job. With this, I am going to stop. I hope the example kind of gave you an insight of how to work with open circuit time constants and what to do about them. All right. Thank you.